Hi, amplifiers are classified depending on different parameters. One of the parameters is where the quiscent or operating point is fixed and how much the magnitude of the input signal is. Accordingly, there are four classes of operation for BJT. These operations are class A, class B, class AB, and class C. Let us understand these operations. In the beginning, we will see the basic fundamental. We have two sources connected in series, AC source and DC source. At the output of this combination, we will get waveform as shown through the animation. Let us assume the value of DC supply as 2 volt and of the AC supply as 2 volt peak to peak. Now let us see waveform which we get. This is x-axis and y-axis. This is DC output 2 volt and AC waveform is riding on that 2 volt. Let us write down the values. This is 0 volt reference. This is 2 volt DC line. And this is AC signal which is of 2 volt peak to peak. Now let us write here value as 1 volt and value here as minus 1 volt. Now see what happens to the waveform when we change the DC value. Suppose I make DC voltage as 1 volt and I am keeping this signal as it is. When this is done, see the waveform. When value of DC signal is reduced, waveform gets shifted downwards. Now suppose I make it 0 volt. If you see the waveform now, it will be shifted down. And finally, if I make it minus 1 volt, and if I see the waveform is shifted again. So what it is showing that AC signal gets shifted by the DC magnitude, and this concept would be very useful while understanding the classes of operation. This is common emitter configuration circuit. We will apply input to this circuit across base and emitter, which is a series combination of AC and DC. Once we apply the input, then we will see the current IC in the output and the collector emitter voltage VCE. But before applying input, let us quickly revisit the basic principle of transistor. In transistor, collector current IC is directly proportional to IB. That means if IB increases, IC increases. If IB decreases, IC decreases. Now this IB, how do we get? The base emitter voltage of the transistor, that is known as VBE, is 0.7 volt if it is a silicon transistor, and it is 0.3 volt if it is germanium. Let us assume this transistor as silicon. If input voltage is more than 0.7 volt, then only current IB flows. We are having here the series combination of AC and DC. Let us see if we keep AC 2 volt peak to peak and DC as 2 volt, our IB will flow or not. If IB flows, then IC will definitely flowing. Let us see it by graph. Say we are having one green line shown. Let us write there as 0.7 volt. This is indicating VBE. Now see the input. Input is series combination of DC and AC. This red line is 2 volt and this cycle is 2 volt peak to peak. Now if you see it properly, this waveform, this value is always greater than 0.7 volt. And what is our basic principle? If this voltage is more than 0.7 volt, IB will be flowing. And if IB flows, IC is going to flow. So from this graph it is clear that for full cycle IB is flowing. So for full cycle IC will be flowing. This is what is our current IC. So current IC is flowing from 0 degree to 360 degree. If we draw the graph for VCE, it would be like this. This is the graph for VCE. It is inverted because it is common emitter configuration. What is our conclusion from this discussion is that IB is flowing for full cycle. So the current IC is flowing for full cycle. So this type of operation is known as class A operation, in which transistor remains in active region throughout the AC cycle and the output current flows for 360 degrees. Now let's see the next class of operation. We have same circuit and we are connecting the same input. We are having AC and DC in series combination. Let us take the value of AC as it is 2 volt peak to peak. We are going to make the value of DC to 0.7 volt instead of 2 volt. When we make it 0.7 volt, let us see what happens to IB and hence finally what happens to IC and VCE. Let us see it graphically. This is as usual our reference line of 0.7 volt, that is VBE, and this is our input signal when our DC is 2 volt and AC input is 2 volt peak to peak. But now we are making it 0.7. So let us see through animation that what happens to this waveform when it is made 0.7 volt. So this has come down. Now you can see that 0.7 volt your reference line of VBE. Above that this half cycle is there. That means IB will be flowing only for this half cycle. And this cycle is below 0.7, and as per our basic principle, when input is less than 0.7, IB will not flow. If it is more than 0.7, then only IB flows. So only for this half cycle IB flows, and for this half cycle IB does not flow. And according to our basic principle, when there is IB, there is IC. So the output IC would be like this. It would be only for half cycle. There will be no IC for this cycle. And if we draw the graph for VCE, it would be like this. Again, it is inverted due to common emitter configuration. So what is our conclusion from this is we will get current only for half the cycle. This class of operation is known as class B operation. The transistor remains in active region only for the half cycle. The output current flows only for 180 degree. Now let us see next class of operation. Now we will keep the AC input value as 2 volt peak to peak as it is. And now we will change the value of DC voltage. When we kept DC voltage 2 volt, we got class A operation. And when we kept it 0.7 volt, we got class B operation. Now we will keep the value in between. Let us this value is 1.2 volt. Now let us see what happens to IB and then to IC and VCE. So let us see it graphically. This green line indicates our 0.7 volt VBE, and now this is our input signal. This input signal DC value is 2 volt, and now we will make it 1.2. Now see, this value is now 1.2 volt. Now you can see the waveform which is above 0.7 is this one. That means for this much of waveform, IB is flowing, and for this part, IB is not flowing. So IC depends on IB. The waveform for IC would be like this. It is obvious because for this much part, IB is flowing. So there is IC for that. So we can say output current flows for more than 180 degree but less than 360 degrees. Now see the waveform for VCE. It is inverted because of common emitter configuration. So we can conclude that it is class AB operation. In this, transistor remains in active region for more than half the cycle but less than whole cycle. And the output current flows for more than 180 degree but less than 360 degrees. Now let's move to the last class of operation. Now we will keep AC input as it is 2 volt peak to peak, and we will change the DC voltage. When we kept DC voltage 2 volt, we got class A operation. When we kept it 1.2 volt, we got class AB. When it was 0.7 volt, we got class B operation. Now let us keep it is 0.4 volt and let's see what operation we get. When we keep it 0.4 volt, let's check IB and then go for IC and VCE. Let us see it graphically. This is our 0.7 volt base to emitter voltage. This is our input signal. Let us take it down to 0.4 volt. Now this value is 0.4. Now from this waveform, what we get? That is above 0.7 volt, this much part is there. That means for this part only IB flows. That means IB is flowing only for less than 180 degree. Now if you see the IC is also flowing less than 180 degree. And if you see now VCE, it is inverted waveform due to common emitter configuration. So what we get by keeping DC voltage 0.4, we get the operation known as class C operation. In this, transistor remains in active region for less than half cycle and the output current flows for less than 180 degree. Now for 0.4, we are getting class C operation. So these 4 operations we got by changing the DC voltage. Now all the operations we have seen theoretically. Let us see all these classes practically in the next slide. It is AC generator producing 2 volt peak to peak sine wave. We have DC source which is kept at 2 volt. Now these two signals are displayed on the CRO screen. This is 0 volt reference line. In the beginning we will connect the sine wave to the CRO. So this is what is our sine wave. and this sine wave is having value 2 volt peak to peak. It is riding on this 0 volt reference line. Now we'll connect DC signal to the CRO. So again we will go back to the 0 volt reference line. Now this line will be shifted up by 2 divisions, and this is our 2 volt signal. And now we will connect AC and DC in series, and that signal will be displayed on the screen. Now you can see sine wave is riding on the 2 volt reference line. Now this is our input signal which will be applied to our circuit. This is applied at the base terminal of the circuit, and we are taking output from this circuit. We are connecting around 10.5 volt across collector and emitter, and output of this circuit is connected to the CRO channel number 2. And now this output, it is displayed on the screen. What we are getting here, output is 180 degree out of phase. This is due to common emitter configuration. Now this is known as class A operation because transistor remains in active region for full cycle, that is 360 degrees, and output current flows for 360 degrees. So this is class A operation. Let us go for class B operation. Now we will reduce this 2 volt DC bias to 0.7 volt. Now we will off the channel 2, and now see the input signal. When we reduce it to 0.7, it gets down to the 0.7 volt. So AC signal is getting shifted downwards to the 0.7 volt. Now this is shifted. Now you can see it is around 0.7 volt on the DC source. And now see the output signal. When you see the output signal, what you are getting, half the cycle is cut. That means transistor remains in active region only for 180 degrees. That means output current flows only for half the cycle, that is 180 degree. This is known as class B operation. Now DC bias will increase from 0.7 volt to 1.2 volt. Now this AC signal will be shifted up, and we will keep our DC bias to around 1.2 volt. Now it is the operation between class A and class B. It is known as class AB. What we get here, transistor remains in active region for more than 180 degree but less than 360 degrees. That means output current flows between 180 degree and 360 degrees. Now let us go for last operation, that is class C operation. We will reduce our DC bias less than 0.7 volt, that is approximately 0.5 volt. So what we get here is, we get the output waveform like this. In this case, transistor remains active for less than half cycle. That means output current flows for less than half cycle. This is what is known as class C operation. I have used this circuit for the practicals which we have seen in the previous slide. In actual practice, this circuit is used. What is the difference? Here, DC bias is obtained from voltage divider circuit. This is our voltage divider circuit, where R2 is variable and R1 is constant. This is DC source given. Now, when we vary the R2 between these 2 points, we get different DC bias, and our AC input is connected at this point. Now we get same effect of this AC and DC combination. Both the circuits give same output. Thank you very much for watching my video. If you are satisfied, please do like, share and subscribe to my channel. Thank you once again.